spend just a few minutes talking about the calibration of the model, because I think that's a very important and interesting technical component itself. Then show you some of the very, again, I think very preliminary tests that we've been able to conduct to date to try to explore the efficacy of various control strategies. And I'll try to emphasize throughout that we're really not trying to predict in some sense, a disease spread in the sense of who's going to get it. This is very much a more abstract study of, some conditional scenarios, comparing different control strategies within, the abstract world of the model to try to see what the impact of face masks, etc., are. And then, time permitting, I'll bring us back to Toronto and talk about some even more preliminary and very early work where we're actually trying to adapt the Toronto model to investigate some issues. We hear a lot about the models that are being used to look at, try to predict disease spread, and trying to look at different control strategies. And it's in the paper every day. We're seeing what's going on here in Toronto and Ontario. Just yesterday, there were some announcements of, modeling results that are looking very dire, according to the models, if we don't do something more. Huge debates about, how to control the disease while at the same time not completely destroying our economy. There's a lot, the costs of this pandemic are obviously first and foremost health, but also it's wreaking havoc with our economy, which and our lives in many ways. And also, it's not the question of hospitalization. It's not just COVID is the problem, but if operations and normal health procedures are being foregone because we're being overwhelmed by the disease spread, the virus spread, that's hugely problematic. So major debates about what we should be doing. And certainly in this study, we're not answering all of those, but I think we provide, some interesting indications that some of the policies we're talking about, are very important. And so, that's the background we all understand. So when we hear about these models, generally, how are epidemiologists actually trying to predict the spread of something like COVID? And there's many models out there, and some of them are more disaggregated than what I'm showing here. But sort of a classic basic model is what's known as a SIR model, susceptible, infected, removed. So in other words, you can think of our agents, the people, as being in three categories. Anybody who has not had the disease but is healthy is susceptible for infection. There are people who are currently infected, and then there are people who are removed or recovered. They've either recovered from the disease or they die. And so the basic model is actually a very simple little differential equation that's talking about the rate of infection is a function of the current infection level, the current susceptible population, less the people that are recovering. And there's at least two key parameters in this model. So this is a classic feedback loop, a positive feedback, both with positive and negative components and have a couple of key control parameters. But if you notice, this is a very aggregate model. There's no spatial component to it at all. There's no socio-demographics or economics, and also there's no household effects recognition that individuals live within households. So, the disease transmission occurs in two major ways. You're out and about, and you happen to bump into somebody who is infected and have enough of an interaction that you become infected, or you come home and you infect and maybe you infect your household members. And of course, there's other gathering places like work and hospitals and so on and so forth. So the argument is that can we bring a more, first of all, spatially disaggregated view to this model, and second of all, accounting for socioeconomics, and perhaps third, accounting for that within household interaction. And just to illustrate the point, a little cartoon here, because we know, and this is something that's been in the papers a lot of discussion, not everybody is equal in terms of their exposure and their risk. Many of us, all of us are basically working from home. We're doing everything virtually, so we have relatively little exposure. We still have to go shop and these sorts of things, but people who have to go to work, travel on the buses perhaps, but also be in the workplace, higher interaction. Every time we go into a store, there's potential for greater interaction and so forth. And so we know that the actual we can talk about an aggregate transmission rate. We can talk about an average probability of being infected, but in fact, that average is highly, highly, highly skewed. There's some people that, because of where they live or because of what they're doing, are much, much more likely to be exposed than others. And so the question is, can we actually start to drill in at least a little bit to unpack some of this stuff? And we'll talk more about the model in a minute, but the model that, the basic idea is, well, we've been building these agent-based out-of-home activity and travel models for some time, which are purporting to try to model where people are at what point in time in the day, and their activity levels. So can we bring them to this sort of third type methodology to bring that spatial and socioeconomic and household level components to the modeling system. So in principle, almost any, one can imagine a number of these different types of models one could use. In our case, we are using TASHA, which has been developed here over the years. And some of the properties of TASHA, it is a true activity scheduling model. As we'll see, I like to say we wake up people in the morning, we ask them what are they going to do today, and we schedule their out-of-home activities. Again, for this study, I think it's very important from a travel point of view, but modeling point of view, but for this study as well, the model is completely household based. Each person exists within a known household, and there's lots of household interactions being explicitly modeled. From a transportation point of view, it's a tour-based model that we can generate again, the entire activity patterns for the day can give rise to complex tours that we model on that basis from a travel point of view. It is fully agent-based. We synthesize an entire population for the region. Every person within every household is explicit in the model. And as I say, we model everybody person by person, household by household. It is generating activity start times, durations, trip start times, trip end times continuously in time. And as a practical feature, it's been developed actually to take advantage of existing travel survey data. We don't necessarily need very complicated activity-based surveys, although the more detailed, the better. Representation of activities, obviously, the better. So the model in the Toronto case has been built off of Transportation Tomorrow survey data. So just to illustrate very, very loosely how this model works, it starts, as I say, we wake up each person and they start with can you see my cursor? Hopefully, I guess it doesn't show up. Does it show up? Yeah. Okay. Good. So everybody starts with a blank slate in the morning, and possibly they don't decide to make any out-of-home activities. But then what we say is that each person will have a set of what we call projects, are things that generate the activity. So if you have a job, you have a work project. If you're a student, you have a school project. Everybody has a shopping project. They might do some shopping, and then we just have another category. This represents a limitation of the TTS data, that TTS doesn't collect trip purposes in much detail other than for shopping, work, and school. So we just have other things you might be doing. If we had better data, this is an example where we had better data of the surveys, we could have a more detailed set of projects here. And so what we have are very extensive probabilistic models that generate what's the probability that a person is going to go to work today. If they do decide to go to work, what is their desired work start time, and how long do they desire to the duration of that work trip. And so we generate a set of activity episodes within these various projects that people would like to participate in, and then we proceed. We then proceed to schedule them, and as we schedule them, trips are emergent. So in order to get from home to work, you have to make a trip. So we generate a trip from home to work, and then we do this kind of incrementally. If you have nothing else to do that day after you finish an episode, you return home. So when we schedule the work episode, we insert a trip from home to work and a trip from work to home. But and we just continue to do that, and as we do that, we build the schedule over the day, and trips, tours, trip chains emerge out of that scheduling process. And so what we end up with at the end of this stage is a feasible schedule for this person that involves 0 to n home-based tours, which may also have intermediate sub-tours as well. So there's the complexity of a daily activity pattern is generated out of this simulation process. Once we have the tours, we have a tour-based mode choice model that then on a tour basis decides are people going to drive or bike or take other modes of transit. This is actually a probit model, so that the tour utility is the sum of the individual trip utilities. Each trip has a random error term. We make it a probit model so that when we add up the random utilities for each trip, the error terms remain normal. So we end up with a normally distributed tour utility for each of the possible feasible tours. So this gives us great flexibilities. We don't have to hardwire some sort of nested logit model, for example, to represent the various modal combinations. I mentioned households. We have a lot of household level interactions, joint activities between household members, allocation of cars when there's conflicts. Example here is showing there's 3 drivers, only 2 cars, who gets the cars? And then we have within household ride sharing that's all sorted out. The TASHA is implemented within what we call GTA model. TASHA schedules a day for people, but TASHA assumes we know where they work, where they go to school. It assumes we know the attributes of the persons, and then eventually those trips have to be assigned to road and transit systems. So we have built GTA model, which is an overall model system for doing activity and travel modeling. TASHA is the core. And this is what it looks like. In some sense, it's a very conventional sort of model structure where we iterate through, we assume a set of travel times, generate activities and trips and so forth, assign them to the network, and then iterate the new times around. But this is showing that in order to run TASHA, we need to synthesize the population. We need to assign for each place of residence, place of residence, place of work linkages, place of residence, place of school linkages, and so forth. And as I mentioned here, this model is actually operational within the GTA and is being used by most municipalities. We're also using it in some research applications elsewhere, including Sydney. And so this actually gets us to the case study. Colleagues at the University of New South Wales have taken TASHA, and they started working on this before COVID. They wanted to apply it for their own research purposes to the Sydney Greater Metropolitan Area. Then when COVID came, they called me up and said, Eric, let's think about this. Let's try this. And I was kind of skeptical at first, but they talked me into it. So they've actually done the heavy lifting in terms of calibrating, as I'll explain, a SIR model for Sydney based on Sydney data, tied it to TASHA, and then run various tests. So again, the concept we've basically taken the Sydney version of TASHA GTA model. They call it Sydney GMA. Put this new SIR model on top, and I think it's and so that's the basic plan. I think it's very important to stress. I think quite significant limitations. First of all, unfortunately, in transferring TASHA GTA model to Sydney, they basically just took most of the Toronto parameters. So there's been very little actual recalibration of the model specifically to replicate Sydney travel conditions. So I think that's a pretty strong assumption. I think for our purposes, as you'll see in this model, I don't think that affects things too much, but clearly it'd be better if there was a more serious calibration of those travel parameters. The other thing is, this model is bringing I think, a very useful spatial dimension to it, because we're simulating people leaving the home, going to work, going shopping, coming home, whatever. That's a much more detailed spatial representation than in typical models. That spatial representation is at the level of the traffic zone. So all the model is saying is that person A and person B seem to be in the same traffic zone at about the same time of day. So it's not saying person A and person B are in the same office building. They're not in the same store. And so we're obviously not simulating those actual micro to micro, person to person, actual face-to-face interactions that would result in possible disease transmission. But what we are saying is these people are at least in the same vicinity at the same time, which we think is a big step ahead than just saying we don't know where anybody is and we have no idea who's interacting. But I think we have to keep that in mind. Also, the nature of a travel model is, we're modeling people going to work, we're modeling people going shopping, we're modeling other things. We're not modeling going to a wedding on Saturday. We're not modeling going to the funeral home because your grandfather died. We're really probably not modeling, the big party in the mansion out in some suburban location. And we know those are big super spreader events that are the cause of a lot of what's going on. So I think certainly an area for future research is to actually, to what extent can we start thinking about these sort of special generators, these hotspots, super spreader events, and can those be put into the model in some way? I think that would be a big challenge, or maybe we want to be using this sort of modeling strategy to actually try to simulate, the impacts of a super spreader event, again, in some abstract fashion. And in this model implementation, we do model that, well, what if we lock down things, but we're not attempting to change fundamental parameters like I no longer will take the bus because I'm afraid to get on the bus. If the mode choice model says you're going to take a bus because you're making a trip, you might still do that. So I mean, obviously these are quite significant issues, but we're living with it. And frankly, when Taha Rashidi, who's the lead author on this, contacted me, first of all, I said, well, no, we can't do this because of all these things. And he said, well, no, let's continue on. Let's do it anyway. So they did build this integrated model. I'll show the flowchart in a minute. And basically, it steps day by day. It's simulating each day in the life of Sydney, back in the spring and early summer, during the first wave, the first lockdown. And so each day, each agent decides what they're going to do today under the conditions faced by them. They decide whether they're going to wear a face mask. They're going to decide whether they maintain social distancing or not. They go about their business. They experience certain exposures, and this whole thing feeds back on itself. And so the disease state of each agent gets updated based on their experience that day, and we move forward in that way. And so if we think of all the factors affecting what's going on, there are the travel behavior specific parameters. Do I go to work, my propensity to take transit versus drive, and that sort of thing. And again, those are all held constant in this model, and again, largely they're Toronto parameters in this case. Sydney and Toronto are pretty similar regions, so maybe there's some transferability there, but that needs to be tested. We have the disease-specific parameters, the disease transmission parameters in the SIR model. Those have been explicitly calibrated for the Sydney case based on Sydney data that was available at the time. And then, various policy-specific parameters that we will impose on a scenario basis. And so the SIR model, the integrated parameter, the parameters of the integrated system that relate to disease spread were calibrated based on Sydney data. This is using procedures that were developed by one of the co-investigators, Ali Najmi, who in his PhD thesis developed new methods for trying to calibrate large-scale complex model systems such as this. And he actually worked with TASHA. Some of you may have met him. He spent some time here while he was working on his PhD. We've got a couple of papers out documenting the sorts of procedures that he's developed. I don't want to go into all the details, but basically, this is a very major challenge, I think, in travel demand modeling or any large modeling application we can think of, that particularly when you're putting many moving parts together, many individual models that then come together into a model system. How does that model system perform? Trying to calibrate, if you will, how the overall system's performing is a major challenge. What Ali has tried to do is develop some systematic procedures for doing this. Essentially, it has, by and large, has to do with trying to do many model runs to build a bit of a meta model that you can then you then use the parameters of that meta model to try to optimize. That you build a response surface of a meta model, and then you try to optimize the parameters of that seem to give the best fit to the data. So it's kind of a central composite design concept where you systematically pick points in parameter space, and you evaluate the model system there, and you try to interpolate to find the best match to the observed data. It's not, in some sense, it's not dissimilar. Some of you who do state preference work, you set up an experimental design to try to optimize the sorts of questions you're actually asking, to try to explore the parameter space. So these are the parameters that come out, and you can see that there's, and part of it is you to make this thing work, you set a lower bound and upper bound of, you think what's a reasonable range for the parameter, and then again, you're trying to explore what seems to be the optimal parameter value across these various parameters as they interact. So these are the parameters we came up with. So for example, just one that's fairly important, based on the data and based on our model, it appeared that during the time period being examined back in the spring, be the fall in Sydney, there was about almost an 86% compliance rate in terms of social distancing. The Sydney residents seem to be social distancing quite extensively, at least according to, in order to explain the transmission rates we're seeing and the role of social distancing in the model, this would seem to be the case. And so forth, and how much contact is there going on within public transit vehicles and so forth, and what's and so for better or for worse, these are the parameters that came out. But at least as far as we can see, the calibration fit coming out of this model is excellent. So these are very. This is plotting, days of the pandemic, the daily infection rate, and the red dots are simulated, the black dots are observed, and we see that we reproduce the daily infection rates very, very clearly, and this is also showing it as cumulative infections, and this is showing how it breaks down by stages, which seems to be very, very plausible. So we were quite happy with the calibration fit. This shows the overall flow chart, the logic in the simulation model that goes day by day. Is depending on one state, one is exposed to different things, and again, this just cranks through. So let's look at some of the tests we did. So and in all these tests, it's kind of, again, sort of a conditional test. We know what happened in Sydney during these early days of the first wave. So we know what happened. So we have that base case that the model's been calibrated to, and then we will change something, and we'll parametrically change something like the social distancing rate. What if people weren't social distancing at 86%? What if only 50% of the people are social distancing? What would be the impact on the daily infections and cumulative infections? So for example, this is showing for different percentages, the color coding on the lines is for different percentages of average social distancing, what do the daily infections look like? And as not surprisingly, as the social distancing rate goes down, the time period the time period for the period of sort of active infections spreads out. Similarly, if we look at, Sydney, like what happened here, they locked down. What if they had waited? What if they had waited a week or 2 weeks later before locking down, or what if they had locked down earlier? What's the impact on total cumulative number of cases? And number of cases, and so quite dramatically, one sees that if they had waited, even a week later, the potential spread would have been much more dramatic than it was. So timing that lockdown is very important. If you wait too long, and we hear this from the epidemiologists all the time, if you wait too long, it's an exponential growth. According to that differential equation, you're going to get massive uncontrolled growth. It's going to be very difficult to control. So home quarantining. What if you weren't as rigorous in terms of quarantining people? Again, we see the same sort of behavior. So I think in all of these, what we're seeing is behavior that is consistent with our intuition. It's consistent with what the public health people are telling us. But this, I think the advantage of this is helping to quantify that, to illustrate the differences and ranges of impact, again, within at least this abstract world we're working in. Face masks are very, very important. The impact of what's the percentage of people who wear face masks outside the home. Very, very big impacts as we would expect, as we're being told. They also tested face masks at home. I mean, this was something, I don't think I would have bothered testing this one. I can't imagine people being willing to wear a face mask at home. Fortunately, it turns out that really has very little impact. So that's not a policy I think we need to recommend. Anyway, some of the key findings, which again, I think are very consistent with the messages we hear from other sources who know a lot more about disease spread than we do, is that social distancing needs to be, we need to have a significant majority of people social distancing if it's going to have any impact. And we're not going to be in bad shape. And in particular, that threshold goes up in terms of what's a sort of a minimum acceptable level of social distancing, the more we're letting people to circulate. So again, a very intuitive result, but one I think that reinforces the messages we're hearing. A very dramatic result was this delay in locking down, and in our simulation, you got a 700% increase in cases if they had waited just one more week. Is that the right number? Who knows? But I think it's illustrating the need to impose controls when you need to. Quarantining family members is very, very important. So taking quarantining seriously, and within a household, quarantining strongly within the household is very important. Obviously, the more people are traveling, the greater the risk. And again, wearing masks at home, fortunately, doesn't seem to be an important policy. So these are the people who are doing all the heavy lifting at the Sydney end. And very much appreciate their work. TASHA is the lead investigator there. A grand student. He's a student of Course Mohammedan, was my student. Ali, I've mentioned, was TASHA's student. And Marina McIntyre is the health person on the strategy. We have a couple of papers out under review at the moment on all of this. And just very briefly, so that's the Sydney case study. Happy to answer questions on that. What we're doing here, and this is just very, very, very brief, underway, is the city of Toronto, which I've mentioned. It does use GTA model as their daily, as their operational travel demand modeling system, has asked whether we could generate a modified version that would allow us to explore very much on a scenario basis various what-if questions about different impacts of the pandemic, and particular different control strategies or scenarios as we're trying to unlock or we're trying to recover, and so forth. And so the notion is, can we adjust the model so instead of having the place of residence, place of work, adjusting, changing dynamically within the model, which it normally does in response to all sorts of things. Let's take a base case scenario where we know where pre-pandemic we quote unquote know where people work within the model. Let's fix that. Let's hold that constant and then change things like, well, what percentage of those people are now working from home? What percentage of those people are now unemployed and not working at all? Similarly, if you're going to work, maybe we do adjust a mode choice parameter so the perception of transit is changed. So these would be some, obviously non-work and school activity rates. School, actually trying to, on a scenario basis, adjust these rates to ask what if questions, what would the impact be, but also use this to the extent that we can observe counts and trip rates going on, to what extent can we mimic what seems to be going on out there. So that this is something they've asked us to do. I would very enthusiastic about this sort of more scenario-based testing capability is something I've actually wanted to see in the model system for some time. So I think even post-COVID, having these sorts of capabilities to hold some things fixed to address some policy scenarios, I think is good. So, they came up with a bunch of different things they would like to be able to test or look at, lots of different outputs that are, most of which are the sorts of things the model system is generating anyway. That they'd be interested in looking at. So we have come up with what I've labeled GTA model C19 for COVID-19, a model system design. The idea is that we have our base model, our full model, that we do a no COVID business as usual, kind of counterfactual. What would things look like if we hadn't had COVID, it was just business as usual? Then we with new software, we will impose, so that will generate a complete list of trips. I mean, the output from GTA model, it's a microsimulation model. If we have 7 million people, we have the individual trips by purpose, by mode, by time of day, by origin, by destination for every one of those persons. So we have this massive trip list that represents the base case. So then we can operate on it and say, oh, well, no, you're not going to work, you're working from home. Oh, you're unemployed, you're not going to work. So if you're not going to work, you're not making that work-based shopping trip at noontime because you're not at work. So we can go through and kind of adjust that trip list. But then we may also say, oh, well, you're working at home, but yeah, actually, maybe you may make a walk trip to the local shopping store to pick up some groceries. So we will be imposing adjustments on that trip list to get a new set of trips that we think reflects whatever the scenario assumptions are, represent that. There may also be changes in transit vehicle capacities and different things affecting the performance of the system. And so then we will have a new set of trips that we will generate, will rerun basically the mode choice and the road and transit assignments to get some run results, and then we can compare them to base case. What percentage of transit are we generating relative to the base? What sort of VKT? What sort of greenhouse gases, and so forth? And I should mention, Professor Hatzopoulou has been starting to talk to us about. She's very interested in looking and has already been doing a lot of work on, changes in greenhouse gas emissions pollution because of COVID. So we're hoping to be able to do, emissions modeling on top of this as well. So to do this, we have a two-phase approach. We're just starting phase one, where we're just really trying to build this modified model system and run some very, hypothetical scenarios just to test to see how it's going. But then I think more interestingly, sometime early-ish in the new year, once the COVID survey data is available, Professor Habib is up to his eyeballs running quite a major survey right now, trying to actually observe what the travel behavior is right now. Once that data is available, we will do what we can to do some at least high-level calibration of the model to try to reproduce what the observed fall conditions look like. So we'll have a little firmer ground for for the parameters in this. It can't possibly be a full recalibration. We're hoping to have about 5,000 households for the region. You know, a TT survey has 160,000 households in it. But nevertheless, this will be extremely valuable information to update the model a bit. You know, and then we plan to continue to sort of update this modified version over time to make use of it in various ways. And so, as I say, we're just starting this. I mean, a big challenge is we're actually been talking to all the agencies to try to get whatever road and transit counts we can, both for 2019, so we have a pre-COVID base, and for current 2020 conditions. You know, to the extent that we actually can get transit counts from the TTC, that will really help us, you know, ready the model to see, well, we're 200% off. Well, that's not very good. We do have to code up 2020 road and transit networks, or modify our base 2016 networks. We need to estimate 2020 population employment distributions. So all of that's preliminary work before we can do anything. And maybe just as a bit of an aside, I think this is something for students to recognize, you know, to build an operational travel demand modeling system for a big region like Toronto. Probably 90% of the work goes into this sort of stuff, coding transit networks, getting count data, you know, getting the population and employment inputs and all these sorts of things. It's not the sort of thing we tend to teach much in our classes, but this is what we spend a lot of time doing rather than, you know, estimating mode choice model parameters, which is very, very important too. But you know, so there's a lot of heavy lifting that goes on to be able to get these models up and running. We do have to modify our code to implement this new testing scenario. And we'll see what sort of calibration based on the counts we have, and then test various scenarios in anticipation of again next year updating this model. So that's a pretty quick tour of both what we've been doing in Sydney in terms of, you know, trying to look at these control strategies and also starting to modify our existing models here. So I'll stop here. It looks like we still have some time for questions. This is a slide I often like to put up at the end of my presentations. It's a bunch of various miscellaneous pictures of miscellaneous students and postdocs and various people over the years that have been involved one way or the other in some of this work or previous work. And the point of this at the moment is that, you know, we can't be doing any of this right now. We can't be getting together in the pub for a drink. We can't be gathering at a conference. We can't be, you know, at this is one of the, you know, the fall welcoming barbecues that we used to do. So very much looking forward to the day when we've emerged beyond this pandemic and we can actually get together again face to face rather than just me talking at a screen and hoping somebody's there listening. And maybe just one final little note. When I was looking at this, putting this together the other day, in addition to me, there are 13 current professors in this, former students, former postdocs, that are now professors either here or elsewhere around the world. So the prize goes to anybody who can identify all 13 professors other than Eric Miller that are in those pictures. But anyway, so I'll quit here and happy to take any questions from anybody as time permits.
Okay, can I ask a question, Eric?
Sure.
Yeah, well, thanks for this such an excellent presentation. Just an observation I would like to hear you comment about. You said that, you know, I mean, in the transport model, we have only few ways of, you know, capturing the interactions. In this case, and especially in TASHA, two ways it can happen. One, inter-household interaction. One is through shared mode like transit, which ridership went down, I think, during COVID. And the second is being in the same zones, and zones are often way bigger than 3 by 3 meter square stuff. Even that, I see the calibration is almost perfect. So it tells two things. Either we're over and above, I mean, Sydney is assuming everybody behaves like Toronto. So what do you think the calibration is coming so perfect?
Yeah, I mean, it's a really good question. Yeah, I'm perhaps it is so good. But you know, I'm also kind of surprised in some sense how good these SIR models seem to work as well. You know, and they're even more aggregate. So maybe it is that that there are really just some pretty fundamental probabilities here that and almost a law of large numbers kind of things going on. I mean, I mean, the basic premise here is, even though, yeah, it's traffic zone level, being able to kind of, you know, account for the heterogeneity in the population, both in terms of where you are versus where you're not, and your activity levels is helpful. You know, because just being able to say that, you know, to quote, know within the simulation that these two people are at least nearby has to increase their probability of interacting relative to not knowing anything about where they are. But yeah, why the calibration is as good as it is. But you know, I mean, this is a very aggregate. So it's basically, you know, at the end of the day. Let's see if I can go back. You know, at the end of the day, we're saying we're getting the number of cases, we're getting the overall trend in the cases, daily cases, right. So, I mean, that's good. And, but, you know, that's a very aggregate number. You know, we might be completely getting it wrong where those cases are occurring, you know, spatial distribution of them. I mean, you don't know. I mean, I think the very aggregate level for all dynamics is well. That's as far as it goes, and I think that would be all that, you know, the more aggregate models claim. So maybe at this level, the travel model, you know, maybe the travel model is not adding much to it, but at least we're replicating what you can do with the other models. You know, and I guess I do take some comfort in, you know, I think again, whether the actual quantities are correct, the general propensity of the model to generate, you know, these differences makes a lot of intuitive sense. So you might say, well, why do we need the model for that? I think there is still reason to model. You know, I often think that, you know, we spent all this time quite rightly worrying about, you know, trying to get that good fit, you know, worrying about the quantitative, worrying about the numbers. At the end of the day, you end up telling a qualitative story with those numbers, right? So but you have to do all that hard work to get it. Yeah, you know, and I think this issue of calibration is, you know, I think outside of this particular application, I think the same thing happens to our general models. You know, I mean, the classic thing is you calibrate to screen line counts. Well, you know, there's a multitude of sins go into generating that estimate of the screen line count, and the screen line count isn't perfect either. But you know, we tend to say, oh, we've met the screen line count, so it's a good model. There's lots of issues in calibration, shall we say, and assuring ourselves that we build the models for policy analysis, right, and policy sensitivity. So in some sense, I think you know, seeing these sorts of curves gives more confidence in the model than seeing just that we're reproducing the total daily counts.
Just to add comment to that one,
Yeah.
I mean, when the models gives perfect calibration, perfect fit to the observed data, well, my one devil's advocate explanation would be maybe at the macro level, you actually you know, hitting the target by matching the law of large number. Then what scares me is using the detailed model to extrapolate scenarios without explicit you know, representation of the interactions, and in this case, we're not even calibrating the model for Sydney. So that's my comment is.
Yeah, no, and I agree, and I have the same concerns. But I think, you know, again, the results we're presenting are still, in a sense, at a very aggregate level. So we're trying to see, and you know, the point of the model is trying to capture some of the more micro level interactions to see how they affect the macro output. I mean, I certainly would not use this model to try to predict what's the rate of infection in Rose Bay in Sydney, just to pick one suburb that I know of, which happens to be a very high income suburb. I can predict it. It's very low because everybody's working at home there. You know, so I would not be using this model to actually try to predict the spatial distribution in any real sense of who's being not, because I think that would be, you know, particularly at this level of calibration validation very, very difficult. You know, you've probably heard me say it in the day that you know, I think we usually try to model at least one level of disaggregation lower than we believe the results, because we want to add it up. We may believe the results, and I think that's what's going on here to a certain extent.
Thank you.
Yeah, Eric, thanks again. I echo Habib's comment. Really, it's a very ambitious effort, and really congratulations for doing the study. As far as I understand, the TASHA model and the GTA model is a model of a typical weekday, which is drawn or based on the Tts data. And if we want to look at the phenomenon like the spread of COVID-19, perhaps there are variations really between weekdays and weekends, and also seasonal variations. So to move forward, what's your vision really for if hopefully we won't really have COVID for so long, but if we want really to do this and to really capture the variations and you know, have the capability of really generating predictions over an extended periods of time, over let's say 6 months or a year or so on, what would be the modeling requirements for that?
Well, yeah, real good question. I have to confess, to be frank, that I haven't thought a lot about that. We've been busy with other things, but I do think it's I'm not sure actually. Let's say TASHA per se would to go in some sense. I mean, one can think of trying, if one had data, trying to extend it to weekends, but I really do think the big thing are these, you know, super spreader events, propensity for people to come together, whether it's for a wedding or just, you know, a big party on the beach, like you see in Vancouver, or, you know, Trinity Bellwoods a few months ago on the weekend. You know, I think I think we know those are very big events. You know, Donald Trump political rallies, but also another kind of thing is the nursing home system, the long-term care home system, which is a whole different animal, and you know, that's so much of it. So the one thought I have is that you know, I'm obviously a believer in the agent-based microsimulation approach to things, but actually trying to build perhaps more custom models that are trying to model what the dynamics of some of these things. And I think for things like weddings and some of these beaches, it might be, you know, very, in some sense, smaller models in the first instance, or more, let's say, abstracted models. Let's assume 100 people show up at the beach on Saturday afternoon, and we synthesize their characteristics, and then we let them go back out into the population, and maybe that's where our bigger model comes in. And we try to use the model to take this, let's say, hypothesized in some sense, potential super spreader event, and actually try to then model, you know, world, how that would actually play out through the system. And again, to a certain extent, maybe that's just demonstrating, trying to quantify a plausible outcome that kind of verifies what we know, that or we think we know, that, you know, there's going to be a lot of cases coming up. So again, it's not to try to predict that Sally or Sue or Fred become sick out of this, but just trying to illustrate how a super spreader event actually might play out through the community. And I think that might be helpful, first of all, to educate the public. I think it might be helpful to then think about public policies associated with that, if nothing else, just to reinforce how bad these things are. But you need some data because I think the problem with, you know, the sorts of our conventional models, they are typical day. Even though they're microsimulation models, we really are counting on sort of the the simulated values add up to give you kind of correct things. But these super spread events are kind of somewhat rare events. Not everybody has a wedding. They're very idiosyncratic. So trying to predict them in some sort of model like GTA model, I think might be a very difficult thing to do. And of course, we don't have a lot of data for it.
Definitely,
Eric, can I add comment to that?
Yeah, sure.
Questions.
Yeah.
I think the transport models are not designed to capture this type of things, and like fitting one model to all contexts is kind of like oversimplification. My understanding, or the comment would be, if we really want to capture to some level of the spreading phenomena, super spreading event can be exogenously put in the model, and as Eric mentioned, can be interacted. But I think what we lack in our demand model is the social network representation. We talk about a lot of things, but we don't have any model to capture the social network. That's how people meet to each other and spread things. So if we want to develop our model to more generic to this general case study kind of thing, we need to think seriously how to capture social network representation in the model.
Yeah, I would agree absolutely with you. I mean, in TASHA, we have the household network, so the itsy bitsy. But yeah, I agree absolutely. It's your interaction with your neighbors, your friends. And you're absolutely right. I mean, we talk about this, but we have very little,
And computationally, it's almost like impossible. You need some sort of stochastic user equilibrium kind of thing, which is a nightmare to solve.
So and again, these sorts of issues. Again, when Taha first emailed me, these are the sorts of things I was saying. Oh, let's not even try this. But I think it has been a worthwhile effort. But I agree. Yeah. Something like super spreader. As I was sort of trying to say, let's assume one and plop it down, and then at least use the travel model is the best tool available at the moment to, if these people then go back to work or, do one thing or another, how does it work? But I think it's a very zero first order approximation of what's really going on. I mean, another example is international travel. I mean, how did all this start? Somebody arrived at Pearson Airport or at Sydney Airport and they were sick, right? And so the arrival of international travelers to spark this is not something that we're handling here at all.
Thank you so much, Professor Miller, for your presentation. We've passed the 12 p.m. and we would like to thank all the participants and Professor Miller again. And this is the end of the session. Thank you all. Thank you so much. Have a nice day.
Okay, great. Thank you. Bye-bye.
Bye.